Welcome to another deep dive, this time into the world of CERN. You know that place where particle physicists basically just get to go wild? You send us so many articles and notes about what they've been up to, and to be honest, I'm pretty overwhelmed by all the info you send, so we're going to try to break it down together.
It is a lot to get through, but I think we can do it.
Definitely. We're going to look at stuff like a measurement so precise it almost doesn't seem possible. And we'll talk about antimatter. And even a new country that just joined the CERN family. Get ready, because this is going to be good.
I agree. There's so much exciting stuff going on right now at CERN. It's hard to know where to start.
Okay, how about we just go in order? First, CERN's 70th anniversary. That's like 7 decades of pushing the limits of science. Isn't that so cool?
Yeah, it really puts these latest discoveries into perspective.
Totally. Okay. Next up is this measurement that really stood out to me. They were able to measure the lifetime of something called a B0 meson. So, what is that even? And why is measuring its lifetime such a big deal?
Okay, so a B0 is a type of particle that only exists for a tiny fraction of a second. Like, imagine trying to time how long it takes a soap bubble to pop. It's incredibly short-lived. What's remarkable is that the scientists at CERN were able to measure its lifetime with incredible precision, which just shows how sensitive their instruments are and how clever their techniques are.
It sounds like it's not even just the measurement itself,
Yeah.
but how precise they were able to be.
Exactly. Because this precision lets us really test our understanding of the universe at its most fundamental level. This particular measurement helps validate what we call the standard model of particle physics. The standard model is kind of like our best theory of how all the particles and forces in the universe work together.
It's like the rule book for the universe.
Oh, right.
So this measurement fits in with the rule book.
Yeah, exactly. And every time we make a measurement that lines up with the standard model, it gives us more confidence that this theory is on the right track.
But I feel like you're about to say that sometimes they don't line up.
Well, the really exciting part is when the measurements don't quite fit with what we expect. Because that could mean there's something new out there, some new physics that we haven't discovered yet.
So even though this measurement supports the standard model, it kind of sounds like scientists are hoping for some surprises.
Absolutely. We're always looking for those anomalies, those cracks in the foundation that could lead us to new discoveries.
Okay, let's move on to something that really blew my mind. Antimatter. I was reading about this evidence for something called CP violation in baryons and beauty hadrons. I'm not even going to lie. Those words sound like they're straight out of a sci-fi movie.
They do sound a bit intimidating.
Yeah. Can you break it down for me?
Sure. Let's start with the basics. So every particle has an antiparticle, which is kind of like its mirror image, but with the opposite charge. Like an electron has an antiparticle called a positron. For a long time, physicists thought that matter and antimatter behaved symmetrically, but then they discovered CP violation, which means matter and antimatter don't always act like perfect mirror images.
So the mirror is a little wonky. But what does all this have to do with baryons and beauty hadrons?
Well, baryons are a type of particle, like protons and neutrons, the stuff that makes up the matter we see around us. Beauty hadrons are particles that contain a bottom quark, which is another fundamental particle. The interesting thing is that scientists at CERN have observed this CP violation in the way these particles decay, which is a big deal because it helps explain why the universe is made of matter and not antimatter.
Right, so how does that work?
Well, if matter and antimatter were perfectly symmetrical, they would have completely annihilated each other after the Big Bang, and we'd be left with nothing but energy. But the fact that we exist, the fact that the universe is full of matter, means there must have been an imbalance, a slight preference for matter over antimatter. And CP violation provides a way for that imbalance to happen.
Wow, so this little difference, this violation of symmetry, this is the reason we're here?
It's one of the key reasons.
That is a pretty mind-blowing thought.
It really highlights how even the smallest deviations from symmetry can have huge consequences on a cosmic scale.
Okay. On to the next discovery, an ultra-rare particle decay. We're talking odds of less than 1 in 10 billion. That's like finding a specific grain of sand on an entire beach. What's so exciting about these ultra-rare events?
Well, these incredibly rare events are so valuable because they could give us a peek into physics beyond the standard model, like little hints that there might be new particles or forces out there that we haven't discovered yet.
It's like they're whispering secrets about the universe.
Yeah.
We're just starting to listen.
Exactly.
What kind of secrets are they hoping to uncover?
One of the biggest mysteries in physics right now is dark matter and dark energy. We know they make up most of the universe, but we have no idea what they are. Some theories suggest that these rare events could be signs of dark matter particles
Yeah.
or new forces that govern their behavior.
So these tiny little events could hold the key to understanding some of the biggest mysteries in the universe.
It's definitely a possibility.
Before we move on, I have to ask about quantum entanglement. They're observing it at higher energies than ever before.
Yeah.
Can you explain in simple terms what quantum entanglement is and why it's so mind-boggling, especially at these high energies?
Okay, imagine you have two particles that are linked together in a way that goes beyond our normal understanding of space and time. They're connected or entangled, so that even if you separate them by huge distances, measuring one particle will instantly affect the state of the other. It's like having two coins that are magically linked. So if one lands on heads, the other one always lands on tails, no matter how far apart they are.
I'm already losing my mind. So why does it matter that they're seeing entanglement at higher energies?
Well, it suggests that this phenomenon is even more fundamental than we thought. It pushes the boundaries of our understanding of quantum mechanics, and it could have implications for everything from black holes to the very early universe.
Okay, my brain is officially fried. But let's try to keep going. Let's shift gears to the CMS experiment's precise measurement of the W boson mass. Remind me, what is the W boson again?
The W boson is a fundamental particle that plays a really important role in what we call the weak force, one of the four fundamental forces of nature. The weak force is responsible for processes like radioactive decay.
And why is measuring its mass so important?
Measuring the W boson mass with high precision lets us test the consistency of the standard model.
So this is kind of like the B0 Meson lifetime measurement. It's another check to make sure the standard model is still holding up.
Exactly. And the more precise we can get with these measurements, the more rigorously we can test the standard model and look for any tiny discrepancies that might hint at new physics.
Like looking at a painting under a microscope.
Yeah. Each measurement adds another brushstroke to our understanding of the universe.
I love that. Okay. Speaking of new additions, let's welcome Estonia to the CERN family. It's the first Baltic country to become a full member. What does this mean for CERN?
It's really a sign of the power of international collaboration. Estonia's membership brings new perspectives and expertise and resources to CERN. It also allows their scientists and engineers to participate in this cutting-edge research.
So it's a win-win.
Definitely.
Okay, we have covered so much ground. Let's take a quick pause, and then we'll come back and dive into some of the other amazing discoveries coming out of CERN.
So before the break, we were talking about Estonia joining CERN. And it's a big deal, not just because it expands CERN's reach, but it also shows how committed Estonia is to science and technology.
Yeah, it's cool to see a country making science a priority like that. What made Estonia decide to join?
Well, they've been involved in experiments at CERN for years. But becoming a full member means they're even more invested. They're especially interested in research on the fundamental building blocks of matter and in developing new technologies and training new scientists. It's a way for them to raise their profile in the scientific community and attract talented people to STEM fields.
So it's not just about the science itself, it's about the economic and educational benefits too.
Exactly. It's an investment in their future.
Okay. Speaking of the future, we mentioned earlier that CERN is focusing a lot on quantum technologies, especially with the International Year of Quantum Science and Technology coming up in 2025. Can you unpack that a little more? What exactly are quantum technologies, and why is CERN so interested?
Quantum technologies are all about using the principles of quantum mechanics to develop new technologies that could totally revolutionize different fields.
That sounds super cool, but I have to admit, quantum mechanics always makes my head spin.
It's definitely a bit mind-bending.
Can you break it down for me?
Sure. At the heart of quantum mechanics is this idea that matter and energy behave differently at the atomic and subatomic level. The rules of classical physics don't really apply anymore, and things can get very strange. For example, particles can exist in multiple states at the same time. We call this superposition, and they can be linked together in a way that defies our understanding of space and time, which is what we call entanglement.
Okay. I think I'm starting to get it. But how does all this translate into actual technologies?
Well, think about quantum computing. Normal computers use bits, which can be either 0 or 1. But quantum computers use qubits, which can be both 0 and 1 at the same time because of superposition. This lets them do calculations way faster than regular computers.
So it's like a computer that can explore multiple possibilities at once.
Exactly.
What kind of impact could that have?
Oh, the possibilities are huge. Quantum computers could revolutionize drug discovery by simulating how molecules interact. They could help design materials with brand new properties. They could even crack the encryption that protects our online data.
Whoa. Sounds like quantum computing could change everything.
It has the potential to.
What about communication? You mentioned that quantum technologies could change how we communicate too.
Yeah, quantum communication uses entanglement to create super secure channels. Remember how I said that measuring one entangled particle affects the other, no matter how far apart they are?
Yeah.
Well, we can use that to send information in a way that's almost impossible to hack.
So it's like a direct line of communication that no one can intercept.
That's the idea. If someone tries to eavesdrop, it would disrupt the entanglement, and both the sender and receiver would know.
That is mind-blowing.
It is pretty amazing.
Okay, one last question about quantum technologies. What about sensing? How can quantum mechanics help us sense the world around us?
Quantum sensors take advantage of how sensitive quantum systems are to changes in their environment. For example, they can detect tiny variations in gravity, or magnetic fields, or temperature with incredible accuracy.
What kind of applications could that have?
All sorts. Quantum sensors could revolutionize medical imaging by helping doctors detect diseases earlier. They could improve navigation systems by providing more precise location data. They could even help us monitor earthquakes by detecting changes in the Earth's gravitational field.
Wow. It's amazing how quantum mechanics can impact our daily lives.
It's true.
Okay, let's shift gears for a second and think about CERN's 70th anniversary, 70 years of groundbreaking science. What are some of the biggest highlights for you?
Well, of course, there's the discovery of the Higgs boson in 2012. That was a huge deal. It was the missing piece of the standard model, and it confirmed how particles get their mass. It was a real triumph of human ingenuity and collaboration.
I remember that. It was all over the news.
Yeah, it was a big moment for science.
What other milestones stand out?
The invention of the World Wide Web in 1989. It wasn't directly related to particle physics, but it was created at CERN as a way for scientists to share information, and it ended up changing the world.
It's crazy how something that started as a tool for scientists had such a huge impact on everyone.
It is.
Okay, let's talk about the cloud experiment.
Yeah.
It seems like they solved a puzzle about aerosol particles in the atmosphere. How does that research end up at CERN?
The cloud experiment, which stands for Cosmics Leaving Outdoor Droplets, was designed to study how cosmic rays, those high-energy particles from space, might influence cloud formation. It's a cool example of how different fields of science can overlap.
And what did they find?
They found that emissions from trees, especially a chemical called isoprene, play a big role in creating new aerosol particles in the atmosphere. And these particles can then become seeds for clouds, which affects the Earth's climate.
So trees are basically breathing out these tiny particles
Okay.
that help make clouds.
That's a good way to put it.
That's an amazing connection.
It highlights how interconnected everything on Earth is and how important it is to understand these complex systems.
So this research could help us understand climate change better.
Definitely.
It's a perfect example of how basic research can have real-world applications.
It is.
Okay, before we move on to our last segment, I want to mention CERN's new Director General, Professor Mark Thompson. What can you tell us about him and his vision for CERN?
Professor Thompson is a really well-respected physicist. He's a great leader in the field, and he's known for his work in experimental particle physics and his commitment to international collaboration.
What are some of his priorities for CERN?
He's really emphasized the importance of fundamental research in particle physics and exploring new frontiers in quantum technologies and making sure CERN remains a global hub for scientific discovery.
Sounds like exciting times ahead for CERN.
I think so.
We've talked about so much in this segment. From Estonia joining CERN, to quantum technologies, to the cloud experiment. Let's take a quick break, and then we'll wrap up our deep dive by looking at the big picture and what all these discoveries mean for our understanding of the universe.
Okay, welcome back. We've gone pretty deep into all these discoveries at CERN, from super precise measurements to the mysteries of antimatter. It's been a wild ride through the world of science. What really stands out to me is how all these different discoveries come together to tell us more about the universe and how we fit into it.
Yeah, it's amazing how each piece of the puzzle, whether it's measuring the lifetime of a particle or seeing quantum entanglement at these crazy high energies, it all helps us understand the fundamental laws of the cosmos. So let's take a step back for a second and try to sum it all up. What are some of the main things you want our listener to take away from all this?
Well, one big takeaway is just how crucial precision is in science. I mean, the level of accuracy they're achieving at CERN is mind-blowing. It's this precision that lets us test our theories like the standard model with so much rigor.
It's like we're using a microscope to examine the tiniest details of the universe, And each precise measurement helps us see the bigger picture more clearly.
Exactly. Another important thing to remember is how interconnected everything in the universe really is. Like the discovery of CP violation, it links the behavior of these tiny particles to the existence of matter itself and the formation of galaxies. It shows us that even tiny deviations from symmetry can have huge consequences on a cosmic scale.
It's like a domino effect. Even the smallest discoveries can have a ripple effect across the universe.
And we can't forget about the power of global teamwork. CERN is a great example of what humans can do when we work together, driven by our curiosity. Scientists from all over the world are sharing their knowledge and passion to push the boundaries of science.
It's inspiring to see so many brilliant minds working together to try to solve the mysteries of the universe.
It really is. Speaking of mysteries, one that still has physicists scratching their heads is the nature of dark matter and dark energy. We know they're out there, we see their effects on galaxies, but we still don't know what they're made of.
It's almost a little humbling to think about how much we still don't know about the universe.
It is, but that's what makes science so exciting. It's all about exploring the unknown, asking questions, and always seeking new knowledge.
So what is CERN doing to try to figure out dark matter and dark energy?
They're using a bunch of different approaches. One way is to look for new particles that barely interact with regular matter. These could be potential candidates for dark matter. They're also studying the properties of particles we already know really closely, looking for any tiny differences that might hint at the influence of dark matter or dark energy.
It sounds like a real challenge.
It is, but that's the nature of scientific discovery. It takes patience and perseverance and a lot of optimism. But even if finding definitive answers about dark matter and dark energy takes a while, the journey itself is full of valuable insights.
And speaking of journeys, we talked about quantum technologies earlier. It seems like CERN is diving headfirst into this new and exciting world. Can you tell us more about their vision for the future of quantum tech and what kind of impact it could have?
CERN is really exploring the possibilities of quantum technologies in all sorts of areas. Quantum computing is a big one. It could revolutionize things like drug discovery and material science. They're also looking into quantum communication, which could make communication super secure, and quantum sensing, which could help us detect even the tiniest changes in the environment, leading to breakthroughs in things like medical imaging and navigation.
Feels like we're on the verge of a whole new era of technology.
We are, and that's what's so amazing about science. It's a constant exploration, a journey driven by our need to understand the universe and our place in it.
That's a great way to put it. Well, I think this is the perfect place to wrap up our deep dive. Thanks so much for joining us and sharing your knowledge. It's been an incredible journey through the latest discoveries at CERN.
It's been my pleasure, and to our listener, never lose your curiosity, keep exploring, and keep asking questions about the world around you.